We're going to review the oscilloscope, how the oscilloscope is organized, and how do we read the waveforms that come up on the display. All right, so just a brief introduction to an oscilloscope. An oscilloscope is an instrument that we use to analyze and display waveforms, and it usually draws those waveforms with the instantaneous voltages as a function of time. So we'll go over that in more detail. On your standard scope, we're using a Tektronix for this display, but scopes generally all have the same functions. So we have our display, okay, and we have our controls. Scope controls are organized into 4 categories. We have the vertical, horizontal, trigger controls, and the display. All right, those are the typical sets of controls on a scope. So this is your typical scope probe. It's a ×10 scope probe. It connects to the scope with a BNC connector, okay? And that has a calibration little screw on the side. We'll go over that in a minute. Your scope probe has a retractable tip, a ground clip, and the attenuation switch. So ×1, ×10, and the reference setting. So we'll touch on those in a minute, but that is your typical scope probe, okay? So before we start using our scope, in any scope probe, we should compensate the scope probes and make sure they're set up properly. Now, if you remember, when I showed you the scope probe, we have the compensating screw. So we'll connect the scope probe to channel 1, and then we'll connect the ground to the scope. Every scope has a compensation terminal, so we'll connect ground to ground, and we'll connect our probe to the compensation body. So what we have now is a signal displayed on the screen, okay? That's a 5-volt signal at 1 kilohertz square wave. So if the signal is flat across the bottom, then our probe is okay. But if it's not, we need to go into the terminal with a screwdriver and adjust it. So if it's like that, or if it's like that, then you need to adjust it so it comes flat again. Okay? Now, when you're in a school environment, you're always using different probes out of your kits, and you never know who was working on the scope at your desk before your class or after you left. So you should start off every class that uses oscilloscopes by compensating your probes. Okay, so we connect it to channel 1. We connect to channel 1, we connect to ground, we connect to the compensating lug, and we're ready to go. Okay, now, for the purpose of having more clearer demonstrations, we're going to use the simulator to show how to read and analyze signals on your scope. Okay, we use the simulator for that, but I just wanted to give you a rough overview of the scope. There are different scopes out there, and many different scopes, but they all have the same general controls, and the screens all work the same way. So we'll go to that in a second. So we pointed out earlier about the attenuation switch on the side of the scope, on the side of the scope probe, ×1, ×10, and the reference. Okay. Now where those come into play is when it's set to ×1, that means it is loading your circuit with 1 megaohm and about 100 picofarads for most scope probes. Okay. If you're working electronics or sensitive circuits, that will affect the operation of your circuit. If you switch to ×10, it'll load your circuit with 10 megohms and only 10 to 15 picofarads. Now, if you remember your study about loading of meters and that you want voltmeters to be higher internal resistance, you'll see where that comes into play. So most circuits work better if your probe is set to ×10, okay? That's just general. If your probe is not, or if your circuit does not require that, don't do it. But what you need to do is you need to switch your scope probe to times 10. So it's times 1, times 10, and ref. Ref is straight to ground, so I'll give you 0. So if we're on times 10, okay, you need to do it on the scope, then you also need to do it on the oscilloscope. So we're going to switch to that now. So when we want times 10 on the scope, your own scope will tell you how to do it, so you need to figure it out. In this case, Tektronix will hit the channel 1 menu, okay, and it'll say here, probe times 1 voltage, and we can just switch that. Attenuation times 1, switch that to times 10. So we switch it on the scope and on the probe, okay? That'll change the loading of our scope, all right? So how do we read the scope, okay? This scope here is a 4-channel version of the scope I just showed on the simulator. So we have our scope screen. Our scope screen is divided horizontally into 10 divisions and vertically into 8 divisions, okay? Now, horizontally represents time. So each division is worth so much time. Vertically, each division is worth so many volts. So right now we have this set to be worth vertical, using the vertical controls. We set the vertical scale to be 2 volts per division. So I can change that with my volts per division, okay? 1 volt, 2 volts, 5 volts, 10 volts, all right? Then horizontally, we're saying that each division is 200 microseconds. And that can be changed by changing the horizontal scale with our seconds per division control. So we're saying 500, 200, 500, 1 millisecond, 2 milliseconds, okay? So we set the horizontal and vertical scale. And from that, we start to read our signal. Now, here, I see that my signal is going up about 2.5 divisions, back to 0, and then down 2.5 divisions, okay? So the way you measure now is you would say the number of divisions times your volts per division will give you the voltage you're reading. So here, 1, 2, 2.5 divisions times 2 volts per division. So that would say that we have 5 volts peak. 5 volts peak and 5 volts peak. And if we see what we set it to, that is what we have. 5 volts peak is what I set the function generator to. Now, horizontally, one cycle of the wave, one cycle of this sine wave is 1, 2, 3, 4, 5 divisions, okay? So that would be 5 divisions times 200 microseconds per division would give us 1 millisecond, okay? 5 times 200 micro is 1 millisecond, okay? So the period of this wave is 1 millisecond, which means the frequency is 1 over 1 millisecond, which is 1 kilohertz, which is what we have this set to, okay? Now, if you get to a scope and it is either off the screen or it's too low or everything's all squishy, okay? What we typically teach students is adjust your volts per division until you fill the screen without going off it, okay? So right now we're off the screen, so here we're not. Then adjust your time base to get 2 full cycles on the screen. So here we have 2 full cycles. This gives us 1 cycle, okay? It's still okay, just to get your starting position. We try to encourage 2 cycles on the screen and change the horizontal scale so you get as big a wave you can without leaving the screen. All right? So we also have position controls. Right now, the number 1 represents the 0 line for our horizontal scale. So we can change that, okay? We can move this around So now the 0 line is 1 division above the halfway line. Okay, so let's move it back to the middle. We also have horizontal position. So I said before, yeah, this looks about 2.5 divisions, but if we want to be more accurate, we could take this peak and move it along this scale that we have along the middle, so we can see a little more accurately where we are. Okay? If your wave starts to go wonky, we can adjust our trigger level, okay, until it straightens out again. Positioning again. Let's move it. This thing can go the other way. And there we are. Okay. So now we're seeing, in fact, that we are 2.5 divisions. Okay, starting to 0, it is going to 2.5 divisions. So it's 2.5 times 2 volts is 5 volts. Again, one cycle, if we move this again, so the wave starts at a definite starting point. So that's a definite starting point right there where 2 axes cross. And we can say 1 cycle is here. And again, 1, 2, 3, 4, 5, and we're good to go. Okay? So let's change our input signal. Let's say now we want to be 5 kilohertz and 1.5 volts peak. Okay? So we have that. Now, how do we get a good reading on that? Well, first, let's adjust our volts per division and our seconds per division. Okay? Let's do that so we don't leave the screen. We're off the screen, so now we're on the screen. And now let's get 2 cycles. Now, our trigger level tells us where to start the signal on the screen. So right now, if you look up here, our trigger is off the screen, okay? And the trigger level we're at right now is over here. So we're at 2.94 volts. So we are way off the screen. So let's keep decreasing that. Okay, and we should see the arrow. Now the arrow is back on the screen. Okay. And now we're good. Okay, so let's move our wave. So it starts at a definite place. So we are right there. So we have 1 cycle that goes from here to there. 1 cycle that goes from here to there. It's a sine wave. So wherever, as long as it starts and ends at the same place. Okay. So vertically, we have 500 millivolts per division, and we have 1, 2, 3 divisions. So 3 divisions times 500 millivolts is 1.5 volts, which is what we set it to. Horizontally, okay, 1 cycle is 1, 2, 3, 4 divisions. So 4 divisions times 50 microseconds is what our horizontal scale is at. Okay, so 50 microseconds times 4 divisions will give us 200 microseconds, which is 5 kilohertz, which is what we set it to. All right, now, those are easy to do because they're predictable. We set it, okay? We set it on here. If we want to do one more, let's go to 7 kilohertz and 3.6 volts. Okay, let's do that. So again, we can set it to where we want. Now, if we go to volts per division, let's get there. So we're still on the screen. And seconds per division, let's see if we can expand to 2 cycles. Okay, so right there, we're at about 3.5. And then here, we're not quite at 2. So let's leave it there for a second. Okay, let's just leave it there for a second. So at 1 volt per division, we have 1, 2, 3, and we can't quite make that out. So let's move the signal over so we get to where we can measure it. Right there, okay? So right now we're between 3.5 and 3.75 divisions. It's not really accurate. What we can do though is let's lower our 0 point. Let's take this down and let's bring it there. So let's see now if we can go to the next voltage scale. We're at 1. Let's go to 0.5. There. 0.5 kind of goes off the screen, so let's see if we can lower this down to the bottom. Okay. Kind of went off a bit. There. We're at the bottom. Now, we are at 500 millivolts per division. The peak, here's our 0, so the peak is from here to here. So it is 1, 2, 3, 4, 5, 6, 7, 7.25 divisions. Okay? 7.25 divisions times 500 millivolts gives us 3.625 volts. Okay? So we're getting a little more accurate. We're going to go over some settings in a second. I just want to show you. So we're getting a little more accurate. So let's change this back to 1 volt per division. Let's bring this back there. Okay? Now let's measure the period. Let's measure the period. Okay? So we said now that we're at 7 kilohertz. But let's see what we see here. One period of this wave, if we try to go to a good starting point, which is there, okay, it doesn't quite end at a dependable spot. So why don't we expand this a little bit, see if we can get one wave on the screen there. Let's move our positioning. Okay, so now here's the beginning of the cycle, follow through, and there's the end. So it is 1, 2, 3, 4, 5, 6, 7. Okay, so it is 7.2 divisions times 20 microseconds. Okay, that gives us 144 microseconds, and the frequency is 6.94 kilohertz. That is by eye. That is by eye. Okay. Now, most scopes have, let's get this back on the screen, have measurement functions. Okay. So you need to look on your scope how to do those measurement functions. So what you have is measure on this particular scope. So let's measure, okay, and then we could set what we want to measure here. So channel 1. Let's say channel 1, and then the type is, we could say frequency. Okay, so let's leave that one there. Let's set this one, channel 1, type, period. Why not here? Channel 1, type, and let's say max. All right, so that'll be V peak. Okay, that'll be V peak. So what we have here is it is measuring for us. It is saying that our period is 142 microseconds. Our frequency is 7 kilohertz, okay? And our V peak is 3.59. All right? So let's watch on a scope now. Let's add. Look what happens now. Because we don't have enough samples on the screen, it doesn't measure accurately. Okay? Now that we have 2 cycles or more, it makes it a lot easier. And if our volts per division sent our signal off the screen, if it sent the signal off the screen, then that will start becoming inaccurate too later. Okay? So we're using a simulator, but some scopes, everything needs to be on the screen at least 2 cycles to give you accurate measurements. All right? Now there is another tool you can use. There is another tool you can use. And that is the cursor function. Okay? So what happens here is, you can get the cursor function. So in this particular scope, it's here, cursor, what type? You want voltage or time? So do we want to use the cursors to measure vertically or horizontally? Horizontally is time, vertically is voltage. Okay, so let's say time, all right? Let's say time. So we're here, we have that set. So now, using our position knobs for 1 and 2, you need to learn how to do this on your scope, okay? So let's expand this a little more. Let's move one cursor to where this crosses the 0 line right there. And then let's use the other one . Go there. Okay. So what we have now is we've picked the points where the signal crosses the 0 line here, crosses the 0 line there. And right now we have is what delta t is, delta time between the 2 cursors. And it is 144 microseconds, or 6.91 kilohertz. So we're still eyeballing it, but it's a little more accurate, okay? Or what we could do is we could change the type and turn it to voltage. So now the cursors move this way, okay? So now what we could do is, let's bring this to 0, and let's bring that to our peak right there, and we have 3.6 volts. So it'll show you the difference between the 2 cursors. All right, it's a great tool to use. So that was a basic introduction. But how do we connect this to our circuit? How do we connect the scope to our circuit? Okay, so let's go over to that. So we have a little sample circuit here, RC, resistor and a capacitor. Okay, and here's our scope. Now, with your scope, you're connecting to ground, okay? Your ground leads on your probes always connect to ground. So it does not work like a voltmeter where you put your 2 probes across a device to measure. Okay, scopes always measure with respect to ground. So we're gonna take that. So let's connect channel 1 to our source. And let's connect channel 2 to the capacitor. So channel 1 is measuring from here to ground, which is basically across our source. Channel 2 is measuring from this point to ground. So it is measuring across the capacitor. If you need to measure across a specific component, one end of that component has to be connected to ground. If I was to take my probe and just put the ground here across the resistor, I basically take the capacitor out of the circuit, which is not good. So let's start our circuit, and we'll bring our scope back to the screen. So now I have a channel 2 running, and I can turn channel 2 off by going there and turning it back on. Okay, so channel 1, if I had them at the same scale, here's the beauty of a scope. If I had them at the same scale, you can barely see channel 2. Okay? The voltage across channel 2 is very small. All right, and at 7 kilohertz, the reactance of a 1 microfarad capacitor would be simply 22 ohms, okay? So we have 22 ohms in series with 1K, so not much is going to show. But I can change my vertical scale of channel 2 to display it, all right? If you look under my YouTube channel, there is another video on how to measure phase shift using scopes, okay? So you should check that out to measure this phase shift. But back here now, if we want to measure these two, okay, I can go to measure. I could say that for channel 1, source channel 1 type, let's say I want it to be max, okay? We have that. So I have there. Now here, for the second display, I could say I want it to be channel 2 and max, all right? So what I have here is I'm showing that channel 1 has 4 volts max. Let me get another, okay? Has 4 volts max, 4 volts peak, and channel 2 is showing roughly 81 millivolts, okay? So you can measure 2 different waves. Actually, in this scope, on the simulator, you can measure 4. We'll go from there. Now, the frequency doesn't change between the two because they're operating off the same source. So they're both 7 kilohertz as they were before. But that is how you have 2 signals on your screen. You cannot, let me turn this off for a second. You can't have this. What if I wanted to measure V1, VR1? Okay? What if I want to measure VR1? One way you can do it is, there is a math function, okay? Math, and I could say channel 1 plus channel 2, channel 3 plus channel 4. I could change the operation to say minus, and we know that since E is equal to VR1 plus VC1, we know that VR1 would be E minus VC1. So we could say that VR1 could be channel 1 minus channel 2, okay? So now we have an extra signal on the screen. We have an extra signal on the screen. It's not optimal, but it does give you a little bit of a display, okay? Now, another way to do it is we can stop our circuit. If you were experimenting in a lab, and some of the labs do have you do this, we would just simply take these out, and we would just swap our 2 devices because we know they're in series, so that does not really change the voltage in both. So we do this now. What happens here, okay? And then channel 1 goes to my source again, and channel 2 goes to R1, and I can start it up, and now I have to change my, turning that function off. Now channel 2 is there, right? 5 volts sends out, 1 volt sends out the screen. Let's go to 2 volts, and we have a little less than 4 volts across the area. Okay? But if you want to measure a device specifically, you need to put it as the last component in your circuit if you do an experimentation. All right? Again, if you want to learn how to measure phase shift, there is another video posted for that. Okay? And there's also another video posted for measuring DC offset and how that works on the scope. All right? So good luck. Remember, all you need to do to read a scope, all you need to do is look at the vertical scale, the horizontal scale, see how many divisions we take up vertically and horizontally, and you just multiply the number of divisions by the volts or time per division. And If it's not suitable, let's turn channel 2 off. If you don't have a signal that's suitable, then adjust your volts per division and your seconds per division until you get it.